SwayamPrabha. Digital India. Educated India.
Hi, welcome to lecture 30 or the last lecture of the week 6. Today we are going to start a new topic called skin stranger idealization. So all this time we have been studying skin stranger idealization. Before I get into more detail, let me draw an aircraft component. This is the schematic of an aircraft component. Schematic cross section of an aircraft component. So all this while we have been analyzing a beam, a thin walled beam, either open cross section or closed cross section under different form of loading. So we can say that up till now we have studied thin walled beams, thin walled cross section beam, both open and closed cross section, under different forms of loading. So this loading was, we have studied torsion, we have studied bending moment, and we have studied shear forces. So what we did is that we took a thin walled beam like an I section, jet section, C section, or a rectangular section, a cylindrical section. So both open and closed, and we have studied or analyzed such beam structure first under torsional loading, then under bidirectional bending, and then under shear forces. So the torsion produced shear stresses or shear flow, the bending produced direct stresses, and the shear forces produced shear stress or shear flow. What we have done is that we studied the variation of these stresses along the cross section of the beam. This helped us to find out what is the maximum value of these stresses, either normal stress or shear stress, and where does this maximum stress occur. So, this information will later help us to design the beam, to see whether the maximum stress, be it normal stress or shear stress, is the maximum stress below the, including the factor of safety, is it below the ultimate strength or the ultimate or the allowable strength. So, if the maximum stress is below the allowable stress, including the factor of safety, then we said that the beam design is okay and it can be implemented. If we see that the maximum stress developed is more than the allowable stress, then we have to redesign the beam. So, that is what we have been doing all this while. So, we were mostly confined in beams, in thin walled beams, in analyzing thin walled beams. Now, an actual aircraft component, may it be a wing, may it be the flaps, ailerons, skins, anything, or the fuselage itself, will not be beams alone. So, if you look, as we have discussed in detail in the early lectures in the first week of the course, that if you take a cross section of a aerodynamic surface, be it a fuselage, wing, aileron, whatever, then if we look into the cross section will include a thin skin and it will include longitudinal members, which could be longerons for fuselage, it could be stringers for wings, it could be spars, any such longitudinal members. So, an aircraft component is primarily made out of skin and longitudinal reinforcing members like longerons, stringers and spar. Apart from the skin and the longitudinal members, there are transverse members which are ribs and bulkhead, which usually is used to maintain the shape of the component as well as to withstand certain cutouts, certain concentrated load, etc. So, the primary stresses are carried or withstand mostly by these longitudinal members, which are stringers, spars and longerons, and the shear stresses are mostly withstand or taken by the skin. Now, as of now, we have individually studied these stringers or these longerons, and we have individually studied skin. But when we take a full scale component, it is an assembly of several such stringers, which could be I shaped, C shaped, box shaped, anything, embedded in a single cell or multi-scale aerodynamic profile, an aero profile or an aerofoil kind of shape. So, now when you want to analyze the whole aircraft, we have to analyze this whole thing apart from analyzing the beam. So, we have to analyze the beam first and then we have to analyze this whole component. Now, we have seen in our earlier lecture that analyzing a beam is a tedious task. There are rigorous calculations that we have to do. It is very cumbersome and it is very time taking. Now, you can imagine that for a single beam it was so complicated, it was so rigorous. Now, if you have to do it for this entire component which has several such beams and multiple cells, it would become extremely tedious. Now, that is first part of the problem is that. Now, the second part is that when we are at the design stage, when the actual configuration of the structure is not yet fixed, then we have to repeat the calculation several times. For example, we come up with a certain configuration and then we have to check the configuration and see whether it is okay. If it is not okay, then we have to redo the configuration and again check the new configuration. So, this iteration of developing or designing a configuration and testing that has to be done multiple times at the design stage. So, at the design stage, it is impractical and infeasible to do this detailed calculation that we have done, because it is just a it has to go, we have to do such calculations several times. So, at design stage, one would usually prefer to get some rough estimate or ballpark figure of the stresses and strain instead of doing the rigorous calculation. So, that is what skin stranger idealization is for. So, that is what the skin stranger idealization is for. So, we let me then write it down, that skin stranger idealization is for approximate analysis of aircraft components like wing, then flaps, fuselage, tail, etc. So, we have to be aware of these two terms, an approximate analysis and a complete aircraft component. Now, so therefore, in skin stranger idealization, we will be approximating we will make several approximations so that we can get a ballpark analysis of an aircraft component, which is an assembly of several beams or stringer, longerons parts and the skin, and it could be single celled or multi-celled. So, that is what is meant by skin stranger and analyzing. So, after saying all this, I should also mention that the analytical method that we had developed to analyze a beam for under torsional bending and shear force was very tedious. There is no doubt about it. It was very large calculation and cumbersome calculation. But this calculation can be shortened by doing a complete finite element or numerical analysis. So, even if we have a complicated structure like this, we can do a full scale finite element analysis of it. Computational power is very easily available and very cheaper, much cheaper these days because of high performance computing, because of GPU computing, and therefore, doing a full scale analysis of aircraft component, it can be probably easily done, and we might not need to do the rigorous analytical study that we have talked about through the entire course. But there are two issues with that. First is that doing a complete numerical analysis will give us numbers, and to understand whether those numbers are correct and what those numbers physically mean is also very important to successfully design and analyze an aircraft structure. So, just by doing numerical analysis, just by getting numbers which represents the stress, strain and deformation will not solve the entire purpose. we should know the analytical solution to check whether the numbers that we get from the numerical solutions are correct, they are physically acceptable, and what are the physical, and to get physical insight about the behavior or mechanics of the structure. That is one reason why we cannot do a full scale finite element simulation and get rid of the analytical schemes that we have discussed. The second thing is that however easily it is available and however accurate it might be, still there is a sufficient amount of computational cost and time involved in doing this full scale numerical analysis, particularly at the design stage. As I have just discussed, at the design stage there has to be several number of iterations, and we might not need very accurate analysis, but we need quick ballpark or rough estimate of rough analysis of the structural component, so that we can develop the design or we can redo the design or redesign the component. So, that is another reason. So, one reason of choosing skin stringer idealization is that analytical schemes are very cumbersome, numerical schemes do not give us physical insight into the problem, and in the design stage there has to be several iterations. So, and at the design stage we do not need very accurate analysis. Okay. So, if I write it down, the first point is that analytical calculations for an entire component will be extremely tedious and cumbersome. Numerical techniques like finite element do not provide physical insight. So, I should write that alone, like Fe alone do not give physical insight, physical understanding of the problem. Third point is that at design stage multiple iterations and at design stage accurate results are not required. An approximate value would do. So, but saying all this, after the design phase is over, once the configuration is fixed, then of course, a detailed numerical study backed up with a complete analytical study has to be done. That there is of course no substitute for a full scale analytical and a full scale numerical study, but at the design stage it is not feasible. So, these points are the motivation for doing the skin stranger idealization. So, this is why a skin stranger idealization is done. Now, let us move on to understanding what is skin stranger idealization. And so on. So, let me call this as figure 1. Okay. Now, I have drawn these two figures and I am going to explain what they mean. So, the first figure is the actual cross section of an aircraft component. Okay. It, as I said, it has longeron, it has several longitudinal members and it has a skin. Now, as we have discussed in the first week lectures, that the stringers, longerons and spar, that is the longitudinal members, are mostly designed to take the direct stress or the normal stress. Longitudinal members are designed to take most of the direct stress or normal stress, most of the normal stress. And the skin takes mostly shear stress in form of shear flow and a part of normal stress, a small part of normal stress. Right. So, this we have discussed in the first lecture of the first week lecture of the course. Now, all these longitudinal members are going to take mostly the direct stress or normal stress, and the skin is mostly going to take shear stress and the some small portion of the normal stress. Now, what we do is that we consider an approximated cross section which is of the same shape as that of the actual configuration. And then what we do is that usually at the position where the longitudinal members, let me call it as stringers, where the stringers are placed, we place a concentrated area which is called booms. Okay. And we consider that these booms are going to take the entire normal stress and the thick. So, what we do, let me just repeat, at the location where the stringers are there, we are going to place concentrated areas called booms. The booms are going to withstand the entire normal stress and the skin will not withstand any normal stress. So, the area of the boom is going to be area of the stringers at that location, plus some part of the area of the adjoining skin. Now, since this is the case, therefore, we neglect the thickness of the skin, because the entire area has now been shifted to the boom, and therefore, we neglect the thickness of the skin. Skin thickness is neglected. And the skin is going to take the entire shear stress. So, if I summarize this, the boom is going to take the entire normal stress, whereas the skin is going to take the entire shear stress. So, if we summarize what we have discussed is that in skin stringer idealization, okay, the booms will withstand the entire normal stress to the thickness of the skin and the skin takes the entire shear stress. Next, we will be in the next lecture, we will be discussing this further and discuss the implications of this idealization and how it helps us to get quick solutions of the problem. Thank you.